All of you who had AP Physics 1 last year learned conservation of energy. And some of you have been attempting to use the rules of conservation of energy on the questions we've had so far these last couple of days. And in some circumstances, that's fine. But if you've noticed, I've been very deliberate in not talking about conservation of energy. That is not because I don't want to. I do want to cover the topic of conservation of energy. But just to be upfront and honest, you don't need it. Every one of these problems can be solved by just tracing the energy. So the idea of conservation of energy does help in certain circumstances. But if you don't understand what I mean by tracing the energy, then the concept of conservation of energy will just be something that you apply in the wrong circumstances, and therefore will be unable to fulfill what you will have to do on the homework, or perhaps on an exam. And energy is always true. That doesn't mean that it means anything useful. Because just because energy is conserved doesn't mean you can trace where it went. In fact, we often use conservation of energy to try and figure out how much of the energy went places we didn't expect. We say it's a universal law, add up all the energy we do know, and compare it to how much we started at the beginning. And then we know, well, some of it went somewhere. Let's go trace it and find it. When we say conservation of mechanical energy, we're only talking about three things: gravitational potential, elastic potential, and kinetic. So when we talk about conservation of energy in here and we use it as a topic, but the truth is we only really use conservation of mechanical energy in practice to do calculations. And in order for us to be able to use that, we have to know that there's no external force acting on the system to which energy could be leaked away. Meaning something that is doing work that is in gravity, a spring. Well, that's it. So here's the example we're going to do right now. And this example is mathematically tough. In fact, we can't get the answer. That doesn't mean we can't look at the problem. So I want to look at the problem, but note that we will get to a point where your mathematics will fail you. And I'm okay with that. It's just algebra. But it's pretty big algebra. So I got a block. I'm going to put on this ramp. There's a spring on the ramp at the bottom with the spring constant K. And the ramp has a coefficient of friction between the block and the ramp everywhere of mu. The block is located a distance L away from the spring, and there's an angle theta that the ramp makes with the horizontal. Okay? Any questions about the parameters? I'm going to say that the coefficient of friction is low enough so that the block accelerates down the ramp. So I would like you to figure out by how much is the spring compressed when the block is brought to rest. So I'm just going to move the L to the bottom here because I want you to tell me how many forces will do work on this system. Can we name one? I do think that gravity will do work on this system, yes. Name another force that will do work on this system. I believe the spring will do work on this system. Name another one. Friction will do work on this system. There are other forces that act on this system. Do any of them do work? No, I think these are the only three that are going to do work on the system, which means at the end of this problem, we can figure out the net work on the system by adding up these three forms of work. Some of these forms are likely to be negative. That's okay. I'm doing this problem a little different than we've talked in the past. All right? Now, can somebody give me how should I say this? Can somebody give me a reasonable expectation for what we think the net work will be? Now, I got into a bit of a protracted discussion with Pratyush about this at lunch today. And trying to come to grips, I think his question is not just valid, but it's something I want you all to have an appreciation about. It is clear that this object will both accelerate and then accelerate again, right? It's going to accelerate speeding up and accelerate slowing down. The second acceleration is going to be complicated because it's involving a spring, and the force of a spring is not constant. So this object's actual trajectory and its the manner in which it accelerates is complicated. Wouldn't you agree? However, when we talk about work doesn't take the path into account. It doesn't take what happened specifically into account. It looks at the end and the beginning. If you know that at the very end of your observation, the object is at rest, then you know it has no kinetic energy at the end of its motion. If it had no velocity at the beginning, then you would be able to say the network is zero. Does that make sense? Now, I don't think for a moment the box is going to stay stopped at the bottom of this ramp. I think the spring is going to try and recoil and push the block back up the ramp. And I don't know if the block will make it as high as it once was. I doubt it. I mean, if there was no friction, I think you all realize that the block would just bounce off the spring at the bottom and go back up to where it started from and keep doing that forever. Thus, a conservation of energy system, where the energy is constantly oscillating between kinetic and potential and kinetic over and over and over again. But in all of these systems, we're picking a specific moment in time. Time has nothing to do with these problems, have you noticed? So we are picking a specific moment in time to evaluate. We are picking the moment where the block has hit the spring and compressed it to its maximum. I asked for the maximum compression of the spring. So that instant is the instant that I want to evaluate. And at that instant, the block is at rest. And since it starts at rest and ends at rest, the net work on the system is zero. So all three forms of work will have to sum to be zero. Now, except for the spring force, the frictional force and the gravitational force, can you guys agree with me, will be a constant force during the motion of the object. Let's start with friction. What is the value of the frictional force? We all know that it's going to be in this direction. What would the expression be for the size of this force? All right. So that's my expectation, is that we are no longer in a position where we have to figure that out, that you know it's mu mg cosine theta. If you are not in that position, you need to get into that position. You will not have time on the exam to figure it out. Now, this force acts in opposition to the motion of the object. We need to keep that in mind, that the object is traveling in this direction. So my next question is, through what distance does this force act? L for sure, but is it just L? So we're going to need a placeholder, right? Something that tells us how far the spring is compressed. Is X an okay placeholder for all of you? Yes. All right. So that suggests that this force acts over the distance L plus X, which is good. We're looking for X. At the same time, we know that this force is in the opposite direction of motion, so I must add cosine of 180. I'm not answering that. Now, look, putting the cosine of 180 might be just a little bit of arrogance here. Yes, it is true, but we know this work has to be negative because this work is acting in the opposite direction of our motion. It's taking energy from the system. Friction is slowing the object down. All of those things have to be true. All right, so like I said, I'm not trying to be arrogant. I put the cosine 180 in there because that's the direction it points, right? But we know we're just going to put it, it's just a big negative sign. So I'm not trying to make this so protracted. I'm just trying to make sure that we are being careful. Look, I watch you guys on your quizzes. You're all over the place. Be careful. Lay it out. It's going to be force times distance times the cosine of the angle. Now, if the force isn't constant, you're going to have to integrate. But if it's constant, that's it. So, moving right along, the spring one's easy, right? The spring doesn't act over the whole length. The spring only acts when the object touches the spring. And I can't do kx here. I can't talk about the force in the spring. But we already have an expression for the work done by the spring. A work done by a spring is negative 1/2 kx squared. Now, a lot of you want to put positive there. But look, that's not what we're doing. We're not talking about conservation of energy. This spring took energy from the box. Stopped it. So the work done by the spring on the box is negative. Got it? Excellent. All right. Do you want to do gravity like this? Or do you only want to look at the component of gravity like this? So last class period, they wanted to do just the component. I don't really care. You understand that it won't make a difference, right? Let's make sure we know that, because it's either mg sine theta times whatever delta x there is, times the cosine of, in this case, 0 degrees, or it's mg times delta x times the cosine of, it'd be this angle. I see that as the other angle of that right triangle that's kind of being displayed right there. So that would make it 90 minus theta, which last time I checked is sine theta. Right? So it doesn't matter. I'm not trying, again, it's not me trying to show arrogance. It's me trying to remember that we don't have to break the force up into components. The definition of work does that. And this also means that I can deal with forces that aren't so predictable. I don't want to become complacent, because if some guy's pulling on the block with a rope in that direction, I don't want to become complacent with how I look at angles. Fair enough? All right. So whatever one of these I choose, I'm going to get mg sine theta eventually. And through what distance does this force act? L plus x, that's right. Gravity acts on it all the way to the point where it's compressed and the spring stops. And this is going to be cosine of 0 degrees. All right, so I think we can all agree now I have all contributions to the work, right? So, was not that you had, is that when you're dealing with things like gravity, your reference level has to be taken into account. Many of you would have stopped at mg sine theta times L and forgotten to recognize that gravitational potential energy really has to be based on the lowest point attained by the object. I'm speaking of a different question now. I'm speaking of the idea of potential energy. And potential energy isn't always about where you think 0 is or what's convenient. It's about the lowest point attained by the object. That has to be your consideration. Also, this problem was to put into place the idea that all we're having to do is add the work that's there, trace the energy. Look, we might not have known if the object could be stopped by the spring or not. If we trace the energy, it will tell us. Perhaps the spring can't compress any more than this. Perhaps the box stops before it makes it to the spring. Right? Maybe the gravity was too strong. I don't know. You have to be considering the conditions of your problem. Let me give you an example of that, because that's where we go next. And this problem is going to start out sounding simpler than what you've seen before. Trust me, it's not. Let's get rid of friction. That'll always make it easy, right? Yeah. So I have a box that is a distance h above a spring of spring constant k, and the box has a mass of m. Everybody got the basics? There is no friction here. If you're really paying attention, you realize you could forego talking about the work and kind of come at this problem as a conservation of energy problem. Right? I'm okay with that. If you remember the idea of conservation of energy, that might work for you. If you don't, it's pretty simple. I know the box is going to fall. For example, if I want to know how fast the box is going when it hits the spring, that's not too hard. Right now it has gravitational potential energy because it's above a reference level. We've talked about this before. This is going to be minus the work done to get it there, which is mgh. When it falls, it's going to convert that energy into kinetic. So if I want to figure out how fast it's going, I could just set the energy it has at the top equal to the energy at the bottom. Conservation of energy. Hell, I could figure out how fast it's going at half h if I wanted. At that moment, it would have a little bit of gravitational potential, mgh over 2, and have a little bit of kinetic, 1/2 mv squared. If there's nothing to take energy out of the system, then all of these amounts of energy would have to be equal. Because what the law actually states is that mechanical energy is conserved unless an external force does work on the system. I'll say it again. Mechanical energy is conserved unless an external force does work on the system. That could be positive work or negative work. Look, an escalator is an external force. It does work on the system, getting you to the top of the floor. If it was a slide, then you could take the escalator to the slide and slide right back down. Right? Energy is conserved, except we have to find a way to get you back to the top again. An escalator could do it. But I want to point out that you don't have to think of it this way. Our conversation about work solves every problem. Conservation of energy doesn't. Gravity is going to do work to bring the box down. Right? Work done by gravity will be mg times h times the cosine of 0 degrees. Right? Gravitational force is downwards. The box can go downwards, a distance h. And since they're both in the same direction, that'd be the amount of work done by gravity. Clearly, this is going to lead to a change in the kinetic energy of the box, because it's the only thing doing work on the box. Since the box started from rest, I will get mgh equals 1/2 mv final squared. All right, that is conservation of energy. So I can come at these problems in both directions. Now, you're wondering, what's the catch, Mr. Shelton? You said this was going to be a hard question. Here's the catch. I want you to tell me, where is the box when it's traveling at its fastest? We often forget the big picture. We got so focused on the idea of work, we forgot that acceleration is based on net force. Notice, in all of our conversations about energy, we don't talk about acceleration, hardly at all. We don't care how long it takes for these things to happen. But the truth is, when the box touches the spring, the net force is still downwards, so it's still accelerating. And will continue to accelerate until the net force is 0. When the net force is 0 in any circumstance, that's the moment that the object's velocity has reached a point of extreme. It could be a minimum, could be a maximum. But it's at that moment that it's no longer changing its velocity, when the net force is 0. So the object will continue to accelerate downwards until mg equals kx, which means it will have to compress the spring a distance mg over k. At this point, the velocity is at its maximum. So if I wanted to figure out what is the box's maximum velocity, I would have to reset what I call 0 for the amount of gravitational potential energy the box has. Correct? So let's consider looking at this problem from the standpoint of conservation of energy. For me, I like to look at it as a before and an after. I always like that for conservation of energy. When I release the box, what kind of energy is it going to have? What kind of energy is it going to have?
Gravitational potential.
That's right. That's right. And at the point where it's at maximum velocity, what kind of energy is it going to have?
Kinetic.
And elastic. Right?
Yeah.
It will have two forms of energy. Because the spring is compressed some. Now this side's pretty easy. It's going to have 1/2 mv squared. And it's going to have 1/2 kx squared. But how much potential energy did it have? Well, that would be mgh plus mg over k. Now you can figure out how fast it's going. Look, it doesn't have to have friction and angles to be hard. And this isn't a hard question. You needed to know a piece of information. You knew it, but you needed it kind of thrown in your face. Wouldn't you agree? Yeah. Now, look, I'm trying to be deliberate. I'm trying to be thorough. So because of that, I know some of you are writing things down. Can I erase this real quick? A few of you are still writing. Work on the box. mgh plus mg over k. That's how much work gravity does on the box, because it brings the box from here to there. What else does work on the box? The spring does work on the box. Minus 1/2 kx squared, mg over k. Has to be minus. Has to be minus. Work done by a spring on an object is negative. However, this net work is not zero, so there will be a change in the object's kinetic energy. Right? So mgh plus mg over k minus 1/2 k mg over k squared has to equal 1/2 mv squared minus 0. You see it's the same thing, right? Do you all see it's the same? Yeah. I just got this on the other side now. Conservation of energy is nothing new. And neither is what we've been doing. This is better in that it's clear. You're following and tracing the energy. Now look. All right, so this next one is going to be, and more or less what I'm trying to do is give you guys some foundation for where some of the stuff we're going to use has come from. And so the example I want to use is taking a object, a person on a swing, something like that, and applying only a horizontal force to basically pull them up before you release them. The idea here is that we're going to be doing work because we are clearly applying a force, and that force will be used to move an object. And in this case, the object will be moved against a gravitational field. So some of that work is going to be stored as gravitational potential energy, but also demonstrate how in this particular case, the applied force is not constant. So as you pull on the swing, if you want to move it at constant velocity, then you're going to have to apply an ever increasing amount of force. So the calculation of that work is a little interesting. This is not something you necessarily see on the AP exam, but it is something that once you understand it, you'll understand some of the things we're going to use for the AP exam. Now, there are a couple of things that we have to be a little bit aware of that are different than what we've seen before. This object is not traveling on a straight line. it is instead, I can't even draw that right, it is instead following a curved path. So because of that, we do need to talk a little bit about arc length. A reminder about arc length is that we tend to use capital S for arc length, and S is also written as R times. It can be found by computing R times theta, where this is theta. Oops, this is theta. And in the case of this, we tend to use L for the length of the string. So I think we probably write this as, instead of R times theta, L times theta for the length of the arc that I have there. Now, keep this in mind that before we start talking about work, we are probably going to have to deal with the forces that are acting in the system. There are 3 forces that act in the system: the applied force, the tension, and the weight of the object. If we're going to try and find the work done by the applied force, we need to figure out how much force it actually takes to move an object that is attached to a string like this. And so we are likely going to have to find the size of the applied force in terms of the weight of the object or the tension. It would be best to get in terms of the weight, because the weight is the one thing we can kind of count on. We don't really know the tension, and there's no easy way to measure it or use it, but you guys know that probably in a problem like this, you'd be pretty fair if you were to try and get everything in terms of the weight. That's going to be something that's likely to be given. So I want to start by applying a coordinate system to this, but it's going to be an unusual coordinate system. I'm going to get FA in terms of mg, but I'm trying to get everything also in terms of theta. Now, I could line this up with the cable, and there is an advantage to doing it that way, but I lose something in the future if I do it that way. So for right now, I want to keep it aligned like this. And you may or may not see it the way I do. You could try and do this again with everything aligned with the tension, and there are some advantages to it. You'll get one simplification a little farther down, but I'm going to start here because we've done this problem before, and it'll have the least number of hiccups. What we have, of course, there will be net force in the x direction will be the applied force, and that's going to be equal to T sine theta, or better yet, I should write this as net force in the x direction will be Fa minus T sine theta, and that's going to equal 0, while the net force in the y direction will be T cosine theta minus mg, and that will equal 0. So a little substitution, and you'll be able to show that the applied force is going to be equal to mg tan theta. You guys who don't see that probably should do a little algebra so you can catch up with me there. All right, so now that we know the size of the applied force, I can go about the task of calculating the work done. Now, as I've been talking with my AP1 students, the work is like 3 buckets. For us, it's a sum, but it's still 3 buckets. It's the force, it's the angle, and it's the length. It's these 3 things that are always, at interplay here when we deal with calculating the force. For this one, we're not actually moving some horizontal distance dx, so it would probably be better for us to consider that this is f dot ds times the cosine of theta, because we're going to go some arc length. However, herein lies the problem. A piece of arc here, and a piece of arc here, and a piece of arc here are all in different directions. So as we look at different ds's, we are going to have different thetas. So what I'd really like to do is I would like to actually do this in terms of theta and not in terms of s. And so to understand that, consider this as a piece of arc, ds. That piece of arc, ds, could be put in terms of theta if I just look here and realize that I could write
ds in terms of theta by saying ds is equal to L d theta, where d theta is a little piece of arc, right? A little bit of angle there. So with that in mind, I'm going to write this as the integral of FA dot L d theta times the cosine of theta. Excellent. Now, I'm saying theta here. We got theta here and theta here, but those are not the same theta. So I probably should use some other angle here, some other measure. Let's do that there, because those are not the same. Remember that this angle is the angle between the applied force and, in this case, L d theta. So to see what that actually is, let's go to another page here.
mg sine theta times L plus x minus 1/2 kx squared plus mu mg cosine theta times L plus x times the cosine of 180 degrees, all equals 0. Work from gravity plus work from the spring plus work by friction equals 0. All right, we've added up all three forms of work. Now, here's the part that's just hilarious. We're supposed to be solving for x. I mean, I could distribute. That would be the starting point, mg sine theta times L plus mg sine theta times x minus 1/2 kx squared minus mu mg cosine theta times L minus mu mg cosine theta times x. And I know at this point, some of you are you're just gonna flip out. I really don't care. This is algebra. This is not all that big a deal. So because it's just algebra and because I know things, and I'm hoping you guys do too, I'm seeing terms with x squared, terms with x, and terms without x at all. I'm going to collect terms. So, minus 1/2 kx squared plus mg sine theta minus mu mg cosine theta all times x plus mg sine theta minus mu mg cosine theta times L equals 0. I just collected like terms. Now, I am but an old and feeble man. And clearly, you guys have the brains. I am just a charlatan, but I see ax squared plus bx plus c equals 0. If you really wanted the answer to this, the only way would be to complete the square or use the quadratic formula with this as b, this as c, and this as a. Whoops, not all of that, just this part as a. You could do it. Negative b plus or minus square root of b squared minus 4ac divided by 2a. You could get an answer for x that way. Notice you'll get two answers too, plus or minus. Doesn't make any sense, but one of them suggests that the spring could have been pulled out to meet the block. Remember, the energy is based on x squared, so the energy doesn't know that the spring is compressed or pulled outwards. We would have to know. So if you had a negative answer for x, it's probably incorrect. Now, if I gave you the block was 4 kilograms and gravity was 10 and the coefficient was 0.3 and it was 3 meters above a spring of 600 newtons per meter, you could do the problem, right? So I want to be very clear. Getting to this point was about form, not function. Do we understand each other? This could be on the exam. It would not be on the exam as a symbolic problem where you were looking for an expression. It would be on the exam to ask, how many centimeters is it pushed in? Fair enough? All right. Look, I want to look at another example. I want to increase the level of difficulty. All right? I know you think this was difficult, but the takeaway here, this answer, the takeaway.
Ooh, we don't want to go to that page. Here, this page will do. Let's just get a piece of the string. Let's say the string has been pulled this far already, where we are looking at the string having been pulled a bit to, say, theta. The force we're applying in order to do this is going to be in this direction. That has to be the direction of the applied force. Now, here's the interesting thing. ds is a bit of arc length, but the arc length has to be perpendicular. Is that perpendicular? Not so much. Let's try again. There, that's perpendicular. That's better. The arc length has to be perpendicular to ds. ds is a little tiny piece of arc, but we know that the arc side, the tangent to a curve, is perpendicular to the radius. The string is the radius, and it's defining a curve. So if you put all that together, ds has to be perpendicular to L, which means that this angle is actually going to have to be theta, because this has to be 90 degrees. So although I said it a moment ago, the truth is my integral is going to be FA times L d theta times cosine of, well, it is theta. Now we're going to pull this thing from 0 to some angle in the future. I don't know how far we're going to pull back the swing. That's the catch. We don't know how far we're going to pull back the swing. So we're just going to use some placeholder for how far back we've pulled back the swing. And that placeholder will tell us how much energy we have. So this is it. This is the work done. So let's do a couple substitutions. Substitution number 1. FA is mg tangent theta times the cosine of theta times L times d theta. Well, as we do the work here, I hope that you all see that this is going to be mgl sine theta d theta. Tangent times cosine is sine. These stay the same the whole time, so we'll pull that out front. mgl from 0 to phi of sine theta d theta.
Guys are learning all that fancy calculus about. Because you're learning all that fancy calculus, I'm confident in your abilities to tell me what that is. I am clearly running out of space on this screen, so I'm going to just put the solution there at the bottom, or at least go to the next step. Say this is m.
This is mgl times negative cosine theta evaluated from 0 to phi, where this represents how far back we pull the swing. Okay, so let's go look at the result of this. The work done going to equal mgl times, let's put our limits in, negative cosine phi minus negative cosine 0. So the work equals mgl times 1 minus cosine phi. This is how much work is required to pull back the swing. Now, if you look at my handwritten notes, I find out how much work is done by gravity, and you don't have to do the work to realize that if this is the work from the applied force, the work by gravity would have to be minus mgl, 1 minus cosine phi. And the reason for that is really simple. If the object's being moved at a constant velocity, the net work has to be 0. And also, this also shouldn't be too weird to think of, that the change in potential energy would have to be minus the work done against a conservative force, which is why we get this negative here. We would expect then this object does have some gravitational potential energy. It's higher than it was before. And here's the rub, here's the important part. This is why I spent all this time making you watch this video on a Saturday or a Sunday. Look at the geometry for just a minute. If I take that string and I pull it back a bunch, say we pull it back an amount phi, you know that this whole thing from here to here is L, and this whole thing from here to here is L. But if I were to put a perpendicular line right here, right there, like that, this would actually represent how high the object was lifted. Well, bear with me. This length has got to be cosine phi. So cosine phi times L, or L cosine phi, plus H has to equal L. Or H equals L minus L cosine phi. So lo and behold, the work done in pulling back the swing would be equivalent to how high the swing was lifted, and that would mean that the object pulled back against the swing would have a potential energy equal to mgh. So, weird here, tension doesn't play a role, even though the tension is the reason the whole thing was lifted. The whole thing is based on the weight, and this also means that any time you pull up an object against a string and the string allows the object to fall back into place, you can treat it as though it has a potential energy equivalent to being lifted to that height. That's the takeaway, and that is all over the AP exam, which is why you need to see the theory behind it. You need to know this. It is worth memorizing. It's all over the multiple choice, and I intend to make sure this shows up on your next test. So, homework's posted. You should take a look at it.